So good afternoon, everybody. It's really a pleasure to be again in Vilnius. Thank you, Gedimina. Thank you, everybody. And what I'm going to talk today is a little bit in the process of developing and in the process of discussion. So I will be speaking about dissipatively coupled optical modes, but I will look at it through the prism in the light of PT anti-PT symmetries. So basically what it is about, we look at parity time symmetry, and it exists in two incarnations. You can have either PT symmetric systems where parity time operation commute with a Hamiltonian, and it has very weird property. So it corresponds to non-Hermitian Hamiltonian, so it's non-Hermitian physics, but it can have real eigenspectrum, which is normally not the case for non-Hermitian systems. And it can also exist in the form of anti-PT symmetry, where we have parity time anti-commute with a Hamiltonian. And in this case, we have purely imaginary eigenspectrum. And now kind of warning a bad name, there is also symmetry broken phase, which is also a symmetric phase, despite the name broken symmetry. So basically, we speak here about two possible phases: PT symmetry, anti-PT symmetry, symmetry broken phase PT, symmetry broken phase anti-PT. And it has these exceptional points. And they have extremely weird, again, property, because you have not only spectral degeneracy, which we know also from Hermitian systems where you can have degenerate eigenvalues, but the strange thing here is that also the eigenvectors coalesce. If you have Hermitian physics, you may have point where eigenvalues coincide, but you still have orthogonal eigenvectors, whereas here they also become degenerate. If you think about it in terms of topology, if you imagine, I would start to vary the detuning in energy and the loss gain operation, then you would be able to visualize the topology of these eigenvalues in case of this PT anti-PT symmetry as Riemann sheets intersecting at the exceptional point. Whereas for normal Hermitian situation, you would have two separate cones, reminding the light cones in this case. So I will apply this approach by, wrong button. I will apply this approach now in looking at open quantum systems, so basically chains of bosonic modes which are coupled through dissipation. And the interesting thing is that it provides interesting topological regimes, interesting steady state states, and we also can think about some applications which I will say then next. So our kind of main points we will look at will be quantum engineering in photonics, where we basically engineer leakage channels and try to get something good out of it. Basically, it's redefining dissipation as a tool, as a leverage. And we will look at the symmetry properties in the systems and in steady state dynamics. And this allows for both quantum and more classical phenomena, although it's always difficult to draw the classical quantum border, because on the one hand, we can have some interesting light propagation properties, which you would just need for classical photonics, but you can also think of quantum state transfer or generating non-classical states. So the system itself is bosonic modes, which don't see each other through Van Esteen coupling, but see each other only through coupling to a common reservoir, common Markovian reservoir for simplicity. And this is then the corresponding Lindblad equation. And of course, if you have the simplest case where Lindblad operator is just proportional to the annihilation operator, you have the usual unstructured Markovian reservoir, and in the long term, everything decays to vacuum. But still, there will be, as I will mention, some interesting effects. And you can model this system. It's slightly more difficult to realize something like this. It's much easier to realize it in the following way, where you have a chain where each second mode is sort of a bad mode. So you have lossless modes, in ideal case, lossless modes, and each second mode is strongly lossy. And then you can adiabatically eliminate it, and you effectively get this system. But as I have said, you can make it more interesting. You can make the Lindblad operator a nonlinear function of creation annihilation operators. And this nonlinear loss allows you to, so then your steady state becomes not anymore vacuum. You can drive your system into interesting physical states. For example, you can design quantum states. It can work as quantum source, basically. And again, it's just a Markovian situation. And in this sense, I will start before speaking about chains. So I will speak a little bit about chains as well. But for simplicity, I will show some effects looking at just elementary cell of such a chain where you have two bosonic modes coupled through a common bus. And we will look at collective behavior, which emerges in this case, heat-like flow of light and preserving coherence. And if we add nonlinearity, if these bosonic modes leave, for example, if it's, for example, waveguides, nonlinear waveguides, then we can generate interesting non-classical states. And all this can be seen also in the view of the symmetries. So this is a system. This is my quantities. I look at effective decay rates of the individual modes. If we kind of lift this idealized situations that they are lossless. And then we have also this effective coupling, dissipative coupling. And you can get the system out of this system, eliminated the middle mode, as I have just said. And we have looked at different physical implementations of the system. We have done implementation using laser inscribed waveguides. Or like, for example, here it's more straightforward. If you think about normal indium phosphide integrated stuff, then you would have two good waveguides, and this waveguide, the middle waveguide, is made uniformly lossy by applying a metal strip. So you effectively have this system, and if you've done it right, you can adiabatically eliminate. And one of the characteristic points will be detuning the difference in frequency. So basically, schematically, it's your good modes and your reservoir. So the first point will be what happens if we have, can we reach anti-PT symmetry? And the interesting effects here are equalization, routing, and quantum state transfer. So I can, when I do this, when I describe it using, I can either describe it using Lindblad equation, or equivalently, I can describe it in the language of the coupled modes. And in both cases, I can rewrite, kind of including the, extracting this global phase. I can extract an effective Hamiltonian, which will look like this. Here is the detuning between the frequencies of my modes. This is all the decay rates. And if I look at the genuine anti-PT Hamiltonian, you see that it resembles the structure very nicely. So what we have here, this is again the energies, and they should have different sign. And we have imaginary couplings. So in this Hamiltonian, this is effectively your complex energies, and this is effectively your coupling constants. So you see it's resembling very nicely. Only kind of the interesting thing here is that normally if people try to do something like this in photonics, they are bound to using systems where you have loss and gain. So basically, then what we have here in attempts to do this anti-PT symmetry and photonic systems, this is gain and loss some active medium. So in our case, we can replace it. We can have completely passive system where this is just my decay rates. And how does it look like? So you get the nicest symmetric properties if you take equal constant coupling case here between these modes. So then you have just one decay parameter, and your Hamiltonian becomes really very straightforward. The control parameter here is the interplay between the coupling, the dissipative coupling, and the detuning in energies. And a very good way, actually, because you still have dissipation, so individual modes lose intensity quite quickly. You need to introduce, so the good way to see what's happening is actually introduce the intensity ratios, because these modes decay, but they decay in a correlated manner. Then you see this typical signature of anti-PT system. So this is the modes, though, decay quickly, but if you look at the ratio, you have this typical oscillatory behavior. So if we look now at the eigenvalues, you see again this typical situation. We have this anti-PT symmetry, so it's purely imaginary spectrum. You see in the PT symmetric phase, the real part of the eigenvalues is 0, and we have purely imaginary eigenvalues. And in anti-PT broken phase, you have complex eigenvalues. Now, so what we see here, again, kind of you, depending on, so basically with the control parameter, you can go from different phases. And here you see changing the values of detuning. I can see different behavior. Here you see the equalization between the modes. Here's kind of you have decay and typical oscillatory behavior. And in terms of the intensity ratio, it's very clear demarcation from oscillatory behavior to just leveling at 1. And this is actually a very interesting phenomena. It's sort of non-trivial phenomena because despite of having open quantum system, you de facto manage to sort of to go in the regime where you counteract your dissipation. So you have the fixed intensity ratio, and you have the equalization. The equalization is actually quite interesting phenomena. So at the exceptional point, it's only asymptotical. But if you are here, the equalization is over the finite range. Why it is interesting? If you, for example, you can extend it also to the chain. Again, kind of, I don't speak much about it. Basically, you have now the sequence of these elementary cells. And again, you will have the anti-PT symmetry, and you will have this dark state. So basically, you are inducing the interference effects, and you will have the antisymmetric dark mode, which will dominate the dynamics. In terms of in the language of, if we now look back how it looks like if we think about in terms of our Lindblad equation and in terms of quantum properties of the system, basically, instead of if you take this chain of waveguides and feed it with just coherent state, you would expect normally that at the output you will get just a statistical mixture. If I feed it with coherent states with different amplitudes, with different amplitudes and phases. But instead of getting into statistical mixture, you have here a pure state at the output. It basically equalizes. You have a flow of correlations through the system. Although your light propagates like diffusively, like heat, it retains coherence, and what you have at the output, you have a pure coherent state. The amplitude of the state is determined by the exact structure of what you have at the output. We have also seen it in the experiment with a smaller chain where you have, this basically plays the role of reservoirs. You can imagine it's waveguides, and the kind of the lossy modes are organized by attaching to each second waveguide an array of waveguides. And we have seen this equalization effect in practice as well. And you can use it if you again go back, you can think about chains, or you can go back to this elementary thing, and you can think about it as a kind of coherent diffusive beam splitter. So the positive side of it would be that it's extremely robust with very small deviation intensity splitting ratio and in phase relation and so on, and it's extremely broadband. We have some, unfortunately, then because of different purely practical reasons, the project a little bit kind of on pent at the moment. But this kind of beam splitters have been inscribed using this indium phosphate by Smart Photonics and into in Eindhoven. And you can also arrange non-reciprocal kind of optical diode where your light propagates in one direction, but basically is not allowed to propagate in the opposite direction. And and different other routing possibilities. For example, you can also think about more complicated structures. Like this is just an example, like a toy example. You can again using these quantum correlations present in the system, this collective behavior. For example, if you initiate this mode initially, then you can, by choosing what you couple in here, you can decide how light is going to propagate. If you kind of, for example, if you inject here coherent light with opposite phases, it will go, all light will go here. Inject coherent light with same phases, all light will go here. Or if you kind of just leave them alone, it will kind of equally propagate and so on. So you can arrange different routing regimes. And another interesting kind of tuning knob which you can use here is, if you think about this, you can keep this coupling constants fixed, but you can actually start to change them to make them time dependent. and use different driving patterns and so on. And in this case, so when you make them, depending how you do it, you can arrange topological and non-topological behavior, and you can transport a state from here to here. Let's look at this toy example. I will not long speak about it, but just a toy example. For example, I have a single photon, and because I want to show it with a single photon, I assume for the moment that these modes are really clean, just dissipation loss. And then I will exploit what I just showed you with this symmetry effects, that I will always have the dark states, negative interference, and lossy sides, so that if I would have just normal evanescent coupling, then it will be just chaotic beating between the modes. If I have my anti-PT symmetry or dissipative coupling, I will have equalization. So the lossy modes will decay, these modes will decay, but these modes, which are my signal modes, they will all equalize. But if I switch on this driven coupling, then my single photon will go from this first side to the last side, to the last mode. And again, here is the question, and you can do it in, either, for example, there are different ways how you can drive. For example, you can only drive the edge couplings, or you can drive each even couplings or each odd couplings. There are different patterns with different properties. This is some, and you can, of course, if you go away from single photon, you can do it with realistic chains, and it is actually quite robust. Now, another interesting point you can do in these systems, normally systems exhibit either only PT symmetry or only anti-PT symmetry. And in this, sometimes people try to play tricks with it, like by using, because parity operator you can define either as sigma X Pauli operator or a sigma Z Pauli operator. And normally, if people want to show that you can have symmetries coexisting, they need to redefine parity operator. In our system, and this was, for example, done in this paper where they changed the definition of parity operators and went from PT to anti-PT. In our case, we can have both PT and anti-PT symmetry by under different mode representation. If we define now collective modes, and this is in principle inspired by the fact that we have seen antisymmetric mode dominates, we define the collective modes. And then I look at the Hamiltonian, and at the moment it's not yet in the form I want to have it, if I think how it should look like, but I can do a kind of gauge transformation, effectively redefining what is my 0 point for dissipation. I can choose it to be 0, or I can choose it to be an average 1 over the kind of dissipative couplings. So basically just changing the reference point, I can make the Hamiltonian, which looks exactly like PT symmetric Hamiltonian. So we have now this condition that this should have different sign, and we have the same coupling. And if you look at this is basically in this way we have revealed our hidden PT symmetries. Also, there's a genuine PT symmetric Hamiltonian. And in this case, my behavior becomes differently. Now, in PT symmetric phase, I have this oscillatory behavior, and in PT broken phase, this type of behavior. And the most interesting effect, if I think about possible quantum applications or possible applications, is the fact that I have in this basis, I have the collective mode, which is basically symmetric mode is always suppressed and antisymmetric dominates. Even if I put all my light into symmetric mode, everything will go out into us. This will be preserved, and all will come out here. In this case, I would like to sit in this symmetry broken phase with complex eigenspectrum. And this makes my open quantum system for this mode de facto a closed system. So this going into this phase makes my system kind of de facto closed. And what I can also want to do now, I want to add nonlinearity in the system. If I add nonlinearity in the system, it will amend my Hamiltonian, and then it depends in which symmetry I am, which modes I want to look at, individual modes or collective modes. So in general, set nonlinearity is a complex, is characterized by a complex coefficient, where this is a usual nonlinear phase accumulation, like kernel, like surface modulation, like kernel linearity that we know, and this is intensity-dependent photon absorption. And we can show that you can basically create out of this effective Hamiltonian of symmetric type. You can get PT symmetry if you de facto have just the real part, and anti-PT symmetry if you de facto have only imaginary part of the nonlinearity. And for us, for example, for generation quantum states as the output, the interesting case in the first place is this one, which we have explored. So we now look at this. We now have nonlinearity. We have a possibility to make my Lindblad operator nonlinear function of creational linear operator. I can either have two photon loss, and two photon loss actually allows, so basically you cannot lose one photon. You will lose photons in pairs. And this makes basically one photon as a steady solution. Uh, what it leads to that your photon number distribution is very quickly narrowing as the light propagates along the waveguide. So you get photon number squeezing, you get sub-Poissonian statistics. And if you would have okay, let's stop it for the moment here. Much more interesting is the nonlinear loss. And in case of nonlinear loss, we can get both narrowing of photon number distribution and generation of photon pairs, depending on how you arrange your system. And we have de facto two types of systems. Again, we are still playing on this effect that in my anti-PT, in my PT broken phase, I have the antisymmetric mode preserved. And I can arrange my system in two different incarnations. If I have symmetric coupling here, then my system can be reduced to just this mode, which is preserved in this mode, which is rapidly decaying coupled to reservoir. If I have antisymmetric coupling, then I will have this reduces just to antisymmetric mode. And here is ideal for generation this quasi single photons, basically light with very, very narrow distribution of photon numbers. And for this, I will need to couple quite strongly this with strong coherent light. And this is in a way a cheap way to get, in many applications in quantum technologies, we now want to use, instead of signal photons, we would like maybe to use something cheaper, like just attenuated coherent pulses. But then this Poisson statistic is quite disturbing. In this case, with the same cheap input of just coherent state and waveguides, you get quite narrow sub-Poissonian up to Mandel parameter 0.8. And in this case, we need to couple with low level of light. And sorry, I forgot to mention, this is how my Lindblad operator depends now on this antisymmetric mode in this case. And these two cases looked into a bit more in detail. For the case that I have this antisymmetric mode coupled, I have this rapid decay, and interesting is this, irrespective of how strong I couple, the decay happens quite quickly and goes into this kind of approaching the single photon. And here we, as I said, we have get up to 0.8 Mandel parameter. A very nice version of photon pairs generation you get here. Again, you just have coherent light, low-level coherent light, but because you have this symmetric mode decaying and antisymmetric mode preserved, if you pump your symmetric mode to generate photon pairs, this pump will be basically by naturally decaying, and your photon pairs are generated in an antisymmetric mode. So you get, of course, it's probabilistic process, but it's actually with quite good probability. We have calculated it, but you have efficient spatial pump self-rejection of around 100 decibel. You don't need filters. You have the small size integrability, and you have these two photons, especially separated modes. This is quantum effects, quantum states which you can get out of this system. So in terms of how you would do it, there are different versions, either this lazy scrap waveguides, or you can kind of, to simplify it, you can try to use the middle waveguide to make it uniformly lossy, just a waved waveguide. This is another indium phosphide platform incarnation. Or what we started to think of but haven't yet done any concrete steps, you can try to use these multi-core fibers and programmabilities that you have there. So basically the general idea here, we try to exploit dissipation, redefined as a resource. In terms of applications, you can think of it as different routing devices, or it's a more classical application, or you can think about in quantum metrology, because at these exceptional points, you have extreme sensitivity. So you can try to use it for sensing. And a part of it, what we are at the moment looking at, is to make a fuller quantum field theory calculation of this model and look for more interesting topological effects and quantum noise. And with this, I would like to thank people who were involved in this work and you for listening.
Thank you very much for a very interesting talk. And we have 3 minutes for questions, please.
Yeah, thanks. It's a great talk. You mentioned single photon sources using basically nonlinear decay, right? So, but is it a single photon or just odd number of photons? I didn't understand why it ends up with single photon.
No, because de facto you have the absorption. Because you have nonlinear absorption,
Yes.
you don't absorb photon by photon. So your absorption goes in pairs. So it makes a single photon. Single photon cannot decay.
You mean eventually it becomes single photon?
Yeah.
Okay,
Of course, we are not
okay.
going as far realistically. I'm not trying to sell it to you a single photon. But what happens is that it leads to extreme quick narrowing of the photon number distribution.
Right. So one photon decays slower than 2 photons. I guess.
Yeah.
So okay. So if you wait long enough, you end up.
Yeah.
Okay. Understood.
Next question. Meanwhile, I would like also to ask, what is the physics? What is the role of this dissipative element in between two main elements? Its role disappears. It's like in stirrup, maybe when.
No, I think one of the main roles is that it's in particular important if we have a chain, because it induces collective behavior. You would have modes pairwise coupled to the same reservoir. It then induces a collective behavior across the whole chain, right? And on the other hand, you can arrange basically you can arrange an interference of these channels again to be able to preserve certain modes you have chosen.
And these dissipative elements do not suck energy because they are on the zero interference, right?
Yeah.
1, 2 more questions. Yes, please.
The populations drop very far, so the ratios, are they very difficult to measure?
Well, I'm confess I'm a theoretician, right? So for me, it's fine to draw the graphs. This we haven't yet implemented in experiment. We're at the moment looking with whom we can do this work experimentally. But what we will you would need to measure something like this only in terms of verifying that you have achieved what you wanted. What we want to exploit is different effects. We just want to make sure we are in these phases.
It's time to thank the speaker again.